Hey guys, it's Mr. Sheeline here. This is going to be the lecture video notes covering the Unit 6.2 notes, sound waves. So this is going to be a decently quick set of notes, though there's going to be some videos in here that I want you guys to watch. So if you're here filling out the notes, good. Just make sure that after or like during this, you've got the other like another window somewhere pulled up, another window pulled up here, so that you have the videos that we're going to watch here. So again, yeah, just after this, make sure you check out those videos. And there's like off the top of my head, I think there's 3 of them. Okay, so here are the learning objectives for this particular set of notes. So define a sound wave and the properties, understand the source of sound waves, understand simple interference, and solve basic wave problems. So we've already been solving basic wave problems, and we're just going to continue solving them here on out. So sound can travel through any kind of matter, but it cannot move through a vacuum because it needs some sort of medium to travel. So in a vacuum, and I'd write this out, by the way, it can't go through a vacuum because there are no molecules for the most part. There is no medium that this energy can travel through in order to produce the sound. Because what are sound waves? They're vibrations of molecules bumping into one another until eventually those vibrations get to your ear. Okay, so because there are no molecules for the most part, because there's no air, you could say, sound can't travel through space. So that's why we can't hear the sun, because what's the sun other than just a million bajillion, an infinite number of explosions just happening all the time. So, okay, the speed of sound does depend upon the medium. So it's the slowest in a gas. Makes sense because I'm here to draw it out real quick, because in a gas you're going to have molecules that look like this. They're kind of spaced out. It's faster in liquids. So I'm going to make it blue for liquid. So in a liquid, it's going to be, they're going to be closer together, and they're going to be in whatever shape of the container. And then, it's the fastest in solids. So, in a solid, they're all going to look like this. They're all tightly packed, and they're whatever the shape of that particular thing is, right? Very rigid, very, not a whole lot of space for movement, super duper tight structure. Okay, so it just makes sense that here, if the sound waves are moving through, if these are our sound waves here, okay, if they require a medium, which they do, if they require a medium, which medium is so much closer that's going to be able to transmit these waves quicker and longer? And it's going to be solids. Now, the only thing is, you're probably thinking, well, Mr. Sheeline, if that's true, why don't we just then speak through like blocks of wood? Why don't we use that? If that's true, why don't we use that in order to communicate? Well, it's one thing for waves to travel the energy. It's another when there is, but then that's where friction comes in. That's where interference comes in. If you have a lot of solids that are disrupting the energy moving through a particular object, eventually the object's not going to transmit anything. Eventually the object's going to absorb all that sound it's going to absorb the sound. It's going to transfer it to friction. It's going to heat up. It's going to expel some of the energy as heat. So there is, it's not to say that solids are the best way to communicate. It's not the best way to transmit the energy in some cases. It just so happens, because the molecules are closer together, that we have just the energy itself moves faster throughout the medium of a solid. So anyway, so here's different, speed of sound in different types of mediums. So here's air at 0 degrees Celsius. So it should be like 0 degrees Celsius right here. So there should be a little C right there, Celsius. Helium, hydrogen, water. And this is all like, look, in water, roughly sound travels through at 1,400 meters per second. It's going to travel through glass at roughly about 4,500 meters per second. It's going to travel through concrete at 3,000 meters per second. Now, again, it depends on how the sound is transmitted. Is it transmitted actually through the material, or is it bouncing off of the material? Because I'm sure some of you are like, wait, hold on. Like, my family has a safe room. My family has a soundproof room, and I know that those soundproof rooms are filled with stuff. Like, there's a lot of concrete in the walls, or there's a lot of insulation in the walls. It's got a lot of drywall. Like, it's padded. It's not a lot of noise gets out. So again, there's a difference between, sound bouncing off of something versus sound transmitted through something. So if it goes through it, roughly speaking, concrete's going to move it pretty quick. Won't go very far, or at least what the sound will sound like won't go terribly far, and you really won't be able to hear it once it then exits the concrete, because it'll just be super duper interfered and just really won't sound like what it did at the very beginning. Okay. So here's the first video. So again, this is going to be a video, and I'm going to pause it here because it's going to just replay to you awful sound quality through my speakers back to the microphone. So give this a watch. So again, this is where I said to have this pulled, the Google Slides pulled up to the side. Give this video a watch. It's going to be a video that's going to show what happens when we add helium to people's mouths while they're playing instruments. So give it a watch, see what helium has to do with and what it does to the sound of the instrument. So give this a watch. It's really quick, and then come back to these notes. Okay. So hopefully you watched the video, and what you saw was that the students that took the helium, once they played the instruments, the pitch of the musical instruments increased, and we'll get to that in just a second. So check your understanding number 1. This is literally the only check your understanding in this whole set of notes. So sound waves travel with the greatest velocity in which kind of medium? We could easily say which one here. It's going to be solids. It's going to travel through solids like it's no one's business, because again, here the makeup of the solid is just arranged in a way that's going to be easier to transmit those sound waves than, say, a gas where there's more space. Okay, so characteristics of a sound. So this is where we're getting to the video you watched a little bit ago. So sound waves are produced by vibrations that occur somewhere between 20 to 20,000 vibrations, or that's just 20 to 20,000 hertz. Okay. So that's the audible range of human beings. There are sounds that are above 20,000. There are sounds that are below 20 hertz, but this is the range that we can hear. Okay. Now, excuse me. Sound waves can be, once they're as they're perceived by us and by other animals. We can talk about loudness, and we can describe the loudness of the sound, and we can describe the pitch of the sound. So loudness is related to the intensity of the sound wave. So meaning, the higher the amplitude, the higher the amount of energy inputted into the system, the higher the volume. So if volume increases, that means you're increasing the amplitude. If you're decreasing the volume, you're decreasing the amplitude. And then there's pitch. Pitch is again what we saw being changed in the Brainiac video a bit ago, where what happened was that the helium increased the helium as it was passing through the instrument kind of thinned the air out a little bit, made it the concentration of it made it a little bit immediately less dense. And so what that changed was the frequency of the sound waves passing through the instrument. So the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. And we're going to see that in a video in just a second here. So again, the audible range of humans are somewhere between 20 hertz to 20,000 hertz, and the upper limit decreases with age. It's not only decreasing with age, it's decreasing per generation, and that's just due to kids like you guys, and this includes myself as well, It includes us using specific technology in a way that we really shouldn't be. So a great example, blasting music through earbuds. Okay, no matter how great the quality is, I'm sure the music sounds awesome. But if you're wearing earbuds and you have the volume almost up to max, you are doing a whole lot of damage to your ears. And we'll get to what damage is being done. But the point being is that we're seeing generational decrease in humans' ability to hear things. It's because you're damaging your ears with, in this case, earbuds. Okay, it's not so much of putting them in as it is with just blasting the music. So this video here, just a heads up, like especially if you are wearing headphones right now listening to this, if you are listening to this through any kind of device, just a fair warning, this video is going to have this YouTube video in the corner here. It's going to show you the range of frequency from 20 hertz to 20,000 hertz. Just be aware that the volume is going to seemingly increase and decrease throughout the video. So there's going to be points where it sounds really loud. And it's not really because it's getting any louder. It's just the frequency is increasing, and it's just you have more of a concentration of noise at one time, if you want to think of it that way. So just be careful of that. But what I want you to do here is I want you to use the video to see where it is when you stop hearing a particular sound. For myself, it's somewhere around 15,000 hertz. I can't hear anything past that. And that's because, again, I grew up using earbuds, blasting music through my earbuds, and also just working with farm equipment without hearing protection. And that's done quite a bit of damage to my ears. So my upper limit is roughly about 15,000 hertz, which is, again, 5,000 hertz less than I should be able to hear at. Okay, so what I want you to do is I want you to see what's your upper limit. At what hertz do you not hear the sound anymore? I just want you to do that on your own there. So again, try it out, see what your upper limit is. Okay, so again, everyone's is the same, roughly speaking, generally speaking, this is the range that we humans should be able to hear. And maybe think about if you're closer to my frequency range. So if you heard only up to 15,000 hertz, if you only were able to hear up to even less than that, maybe think about the things that you're doing. Maybe you're damaging your ears in a way you don't know about. If you were able to hear the sound like pretty much all the way up to 20,000 hertz, awesome. Whatever you're doing, if you're wearing hearing protection around loud equipment, if you are not blasting music through your earbuds or even over the ear headphones, keep it up. Good for you. Okay, because you want to keep that hearing as long as possible, and just be super duper careful. Okay, if you're somewhere between the 15,000, 20,000, again, there's differences in abilities of hearing, whether that is due to the damage on your ear or just the way your ears put together. Because some people just have different ears. Okay, we're going to skip this. And some people just have different ear makeup. So this is the ear. This is how the ear responds to sound. We're just going to kind of go through a super duper quick kind of run through of how it is that you're able to hear. So here is your outer ear right here. Okay. And your ear is specifically designed, like it is evolutionarily designed in such a way that you can hear particular sounds particularly well. A quick little fun fact is that there's a lot of evolutionary biologists that believe that ears are specifically designed in order to hear the sounds that big cats and snakes make. Again, it's just an idea from evolutionary biologists. And there's other tools, if you want to call them that, tools, characteristics on your body that are designed for specific animal interactions that we've been carrying since our ancestors were, or we've been carrying around from ancestors long, thousands and thousands and thousands, tens of thousands of years ago. Okay. So anyway, here's the outer ear, designed in order to concentrate the sound and vibrations towards the inside of your ear. Here you have what's called the tympanum. This is your eardrum. This is going to vibrate, and it's going to send those vibrations here to the hammer, then to the anvil, then to the stirrup. And all three of these guys are the smallest bones in your body, and they're going to vibrate, and they're going to continue to concentrate that noise in a particular way, all the way here to the round and oval windows, little membranes, kind of similar to your eardrum, that will continue to focus and work those vibrations down until it kind of loops through all of these semicircular circles, tubulars. I remember it being called, until it gets here to where you're going to then be able to have some sort of sound transmittable to your brain in the cochlea. So in the cochlea, there are these little hairs. So it kind of looks like this. You've got here's the inside of the cochlea. You have these little hairs in your cochlea that kind of arrange themselves like this. Okay. And there's this fluid. There's this fluid inside your cochlea. And the way it works is that you have the sound vibrations are coming in, and they're going to tickle those sound vibrations. Those sound waves are going to go through this liquid. It's going to vibrate on your hairs. And underneath what's connected to all these hairs is a nerve. And it's going to be this auditory nerve right here. And they're all connected to this nerve, and they're going to tickle themselves, and they're going to transmit a message to the nerve, and then the nerve then goes to your brain. Okay, and then here's your brain. Okay, there's your brain, a little small, but that's your brain right there. And it carries that coded message to your brain, and then in a split, in less than a second, your brain then decodes and then makes sense of what the sound was, or at least attempts to. And that's through speech, that's through any kind of explosion, any kind of noise, tap, sound that you hear out in the open. So the damage that's how, again, super duper quick at how it works. So how does it get damaged? Well, it gets damaged, or it is damaged, can be damaged by just too much noise, too many vibrations. And so for the most part, your stirrups, the semicircular circles or tubulars, your eardrum, for the most part, though it's still very delicate, can take those kinds of sounds. But there are sounds that can completely, where you can you can rupture your eardrum. But I might as well just get rid of the whole thing. But if you produce too much noise, or you're sending too much noise to your eardrum, what you can accidentally do is you can kill off these little hairs. Okay, so the sound waves are way too big, and they're coming across here. And what they do is they flatten out these hairs. And when you flatten those hairs out, they have to stand up right at a particular angle. And when you flatten them, it takes a lot of energy, and sometimes too much energy, for them to stand upright. And eventually they just kind of die. And the awful thing about this is when these hairs die, they don't come back. Okay, they don't regenerate. Once they're gone, they're gone. So that's why it's important that once you start seeing hearing loss, that whatever you're doing, if you're around a lot of loud noises like firearms, like farm equipment, like you're listening to music too loudly, that has to change, because you only have so many little fibrous hairs in your cochlea in order to hear. And the more you lose, the less you're going to be able to hear. So anyway, that's, again, a quick run through of how your brain picks up the sound, why it's important, and to understand, and then also, sorry, not important to understand, but now, and hopefully you understand, if you're starting to lose your hearing, that's why, typically. So the source of sound is going to come from just general vibrations. This little spot here just goes through, musical instruments, with a source of the sound through musical instruments. But all sound has to come from some sort of vibration, whether it is air passing through your throat in a particular way, like I'm doing right now, where you're manipulating the sound using, your mouth, which includes your lips, the top of the roof of your mouth. It includes your tongue, your teeth, okay, maybe your cheeks a little bit. It has to come from some sort of initial source, okay, but that source has to produce those vibrations, okay, because those vibrations are/were energy, okay. And so you have to, again, it's like the conservation of mass. You just can't make things out of nothing. You just can't have energy out of nothing. Energy has to come from somewhere, okay? So it has to come from some sort of source. And then the last couple of slides here, there's constructive interference and destructive interference. So hopefully you recognize this picture right here. This was in the Slinky lab, the Slinky Post lab. And you were asked to draw me a before and after picture. And so here is what the before, you were asked to draw the during and after picture. And so here's the during and here's the after. So during constructive interference, if we have waves that are coming at one another or moving in the same direction, at the point where they meet, they're going to add together like so. And then if they're moving in two opposite directions, like this guy is, they're going to then meet like this, and then they're going to then continue the path way that they were going. So B is going to continue in this direction, while A, while it was initially going this direction, is going to continue moving in this direction. Okay. Now, in the form of sound waves, we could see it like this. So here we've got two speakers. And the speakers are going to, they're emitting a particular amount of sound at a particular frequency. And it's where the tail, it's where this tail here meets up with the blue sound waves as well. And at these little red dots right here, this is where you're going to hear the volume increase. Okay, so right here, this is where volume increases at those little red dots. Okay. And it's just because, again, you have roughly just double the amount of waves hitting at that particular spot. Now, then there's destructive interference. So this is where the waves subtract from one another. So here we have two waves moving in opposite directions on opposite ends of the medium. And so when they meet up, they're going to cancel each other out. And then you're going to go back to your equilibrium position for a split second. And then afterwards, they're then going to continue moving at their normal, for the most part, in the normal direction. Okay. So B is on the bottom. It's moving in this direction. It'll continue to move in that direction at roughly around the same speed. And then A is going to be, it's going to continue moving in its direction as it initially was moving. So, and then how does that look for sound? Well, it looks for sound like this. So at particular positions, so here between for these speakers, in between these sound waves, where they kind of split the difference. So notice that here we've got this line and we've got this line, and there's this empty space in the middle. Well, when this purple line hits it right there, dead center, it's going to be like this. You're not going to hear anything. Okay, and we see that right here and right here, right here, all these little green dots. This is where we see deconstructive interference. And so areas of deconstructive interference, we are going to see what you'll notice is in the case of sound, you're not going to hear anything. Okay. So, and then this is going to finish off with a quick video with showing you the difference between constructive and deconstructive interference. Again, I'm not going to play this, but I want you to watch this to end off these notes. So if you guys have any questions for me still, make sure you ask. Make sure you watch this video at the very end here, and I'll see you guys in the next one.